Okay, sir. So, in experiment 7, sir, was supposed to do the gate driver circuits, and we had two simulations that we had to conduct. One was for the non-isolated, and the other one was for the isolated. So,
Achha, what is the difference between non-isolated and isolated? What is the difference in between isolated and non-isolated gate driver circuit?
in the I don't know about that.
Yeah, Peter, I'm not getting. What happened?
So I don't know about that, sir. The difference. I didn't look into that.
Achha, please explain your circuit.
Yes, sir. So here in the circuit, sir. Sorry, I'm showing something else wrong. So here for the non-isolated, we have 3 op-amps. Here we're having 3 op-amps, some dowels here, 3 op-amps, some dowels here, and some variable resistors here, R4 and R9. And we connect the circuit diagram the way it was given in the experiment in the experiment manual, and we get the output from here, this block here, sir, the VCC block. And
What kind of output you are getting from this block, from this scope?
from the output that's coming, there is one that's triangular, and the other one, I guess.
No, nature of the output. Is it
Yes, sir, there is
continuous?
one.
Is it PWM? Can you simulate it?
Yes, sir, here.
Okay.
So we have one that's triangular.
Simulation results. Can you please explain the simulation results one by one? There are a lot of simulation diagram I can observe here.
Yes, sir. Yes,
Okay,
sir. Yes, sir.
so
Yes, sir.
you make it unchecked one by one. Can you please discuss?
Yes, sir.
What is this?
So this one, sorry, let me start from, let me select all of them. And
What is this waveform?
so let me start with the output, sir. So
Which one is output?
the V out, sir.
And the other one?
The V out, this one will be the output voltage. And for the other one, for the other one, we have.
Anything else?
Yes, sir. So there's this one as well. This one is we get this one. We get the voltage at the op amps. This one, this will be this one will be the voltage at the op amp 1, and this one.
Okay.
This one will be the
Okay, so this is for isolated one or non-isolated one?
Non-isolated one.
So show me the simulation for isolated one.
This one's on.
Okay, the triangular one. What is this? The triangular one?
So the triangular one is the triangular one will be the voltage at top pump 2, sir. So like the first one, this one is the red one, the voltage at top pump 1, then the triangular one of pump 2, and then the output voltage is the one in blue.
Okay, so this is for non-isolated. Isolated one?
So this is for isolated. The
Isolated.
one for non-isolated was one I showed previously.
Okay,
Yes,
okay. Okay, good. Barket, roll number 599. Peter, do you complete that simulation? Do you complete the? Do you complete your report?
No, sir. No, sir. Not yet. I was trying to still do the observation, but in the observation, I was having some problems, so I didn't do it. I want to go through it again and see if I can make some corrections.
Next, roll number 599.
Yes, sir.
Can you please share me your simulation?
Okay, sir.
What happened, Barket? To
I'm
share
sharing.
your complete screen.
This is visible? Hello?
Now it is coming. Explain it and explain me the circuit and that results.
Okay.
What happened?
This one is non-isolated, sir. Hello?
Results?
So this, yeah,
This is non-isolated.
yeah. For that one,
What is your switching frequency? Sorry, what is your frequency? Huh. 1 minute. No. Class, okay. After 4:50. Your class still having no 3:15. Acha, Market.
yes, sir.
I want to increase the frequency of the PWM. Can you please, what is your frequency here? I'm not audible. Am I audible from your end, Barket?
Now it's audible.
Now audible. Okay, I'm asking you, what is your frequency of the triangular waveform? Tell me.
I'm not sure, sir.
You are not sure. Why? Is that simulation is done by you or anybody else?
Maybe 0.1, sir.
0.1 frequency.
Mhm.
Are you sure?
1 kilohertz.
1 kilohertz.
Yeah, the time period 0.1.
Are you sure?
I guess so, sir. Yeah. So maybe 10.
Okay.
Because the time period is 0.1 millisecond. So 1 by 0.1, it will be 10.
Okay, let's see. Okay, Barket.
Okay. Thank you, sir.
Roll number 325.
Yes, sir.
Hmm.
Hello.
Do you prepare your simulation report?
Hello, sir.
Hello. Did
Yes,
you
sir.
prepare your report?
Simulation, sir.
Report?
Report, no, sir. Little more time I need for the report.
Report is not required.
No, I said a little more time I need for the report, sir. I did the simulation.
Acha, show me your simulation. What simulation you have performed? Let me check.
Yes, sir. Just a second. Sir, is it visible?
Make it zoom. Make it zoom.
Hello. More zoom, sir.
This is isolated one or non-isolated?
Yes, sir. Sir, isolated.
Isolated.
Yes, sir.
Acha, what is the purpose for using that isolated gate driver circuit?
Sir, your voice is echoing, sir.
My question is that what is the purpose Okay, for using that isolated type gate driver circuit.
Sir, can you speak a little loudly? I'll put myself on mute.
I'm asking you what is the purpose for using that isolated type gate driver circuit.
Sir, sir. Hello.
Hello.
Sir, in non-isolated, sir, we'll require like a direct connection to the ground. Hello.
No, I'm asking you what is the purpose for using isolated type gate driver circuit.
Sir, for switching high voltages, sir.
What you are telling, I am not getting. Switching high voltage it means what?
Sir, your voice is echoing too much, sir.
Because Guru Gubili, because am I audible from your end?
Yes, sir. You are clearly audible, sir.
Yes, I am clearly
Mine
audible.
it's echoing.
And from students, other students end, am I audible properly?
Hello.
Ritesh? Pratik?
Yes, sir.
Am I audible? Am I properly
Sir,
audible
you're
from your
audible,
end?
but the network in the hostels is a bit laggy today.
So lagging means no problem, but what is the problem? Am I
Sir,
audible?
for me it's echoing, sir. I can hear yours. I can hear you twice.
Acha, can you please explain me in the circuit what you are doing here? Please explain me your circuit.
Sir, we are using an op-amp to generate a triangular waveform.
And from your circuit diagram, what is going on? Please elaborately explain me in your circuit diagram.
Just a second.
Tell me.
Sir,
What
the
happened?
first op-amp acts. Hello.
Please continue.
Yeah. So the first op-amp gives square waves, sir. The first op-amp.
First open gives you the square wave.
Wave. So, yeah, and the second one gives a triangular waveform.
Just a moment. You are telling that first open giving you the square wave. Okay. Can you please check the output of the first open? You have the oscilloscope. Take one oscilloscope. Please take an oscilloscope.
Yes. Just a second.
Take an oscilloscope. Take one oscilloscope. You don't know where is that oscilloscope? Roll number 328. Roll number 328.
Yes, sir.
Can you please share me? Can you please share your simulation to me?
Sir, actually, sir, my laptop is not working. I have messaged you at the starting of the class.
Roll number 331.
Yes, sir.
Please share me your simulation.
Sir, is it visible, sir?
Yes, it is visible.
Okay, sir.
Is it your simulation?
Yes, sir.
Yes, yes, yes. Can you please explain me your circuit?
Okay, sir. It is the output of the fast op-amp. Then this is the output of the second op-amp. Then as a final output, we are getting the PWM waves.
Acha. Which one is the output of the first op-amp? Ramachandra, which one is the output of your first op-amp?
Sir, it is the output of the fast op-amp, sir.
This one. Go to minimize karo. Minimize it. Minimize your grapher. Minimize your grapher. ग्राफर को मिनिमाइज करो. Close it, close it,
Okay, sir.
close it. Close करो. ग्राफर
Okay.
को close करो. Now drag, take one oscilloscope. Now take an oscilloscope.
Okay, sir.
Output okay. Output of this one okay. Acha. So what is your frequency? What is your
So this is 50
PWM frequency?
50 hertz. Sir,
50
hertz.
hertz.
Yes.
How do you know it is 50 hertz? How do you know it is 50 hertz?
Sir, in general it is 50, so I think. So I'm not sure about that.
No. How to find out the frequency? If you are having a signal.
Sir, 1/T.
Now
amplitude.
one of the so what is your T? You are not able to calculate it from this waveform. The T. Are you not able to calculate it?
Sir, I have to simulate it. So I need to find out the output waveform again, then I can find out. Okay, 0.1.
PWM. Go to the PWM.
Sir, it is 10 kilohertz, sir.
10 kilohertz.
Yes.
Okay. Okay, thank you. Do you prepare your report?
But not fully. It is
Ramachandra?
showing waveform side. Sir, not sir. Sir,
Okay. So you are preparing. Achha.
not fully, sir. It is incomplete.
Achha. Okay, okay, thank you. I have posted one PDF in your chat box. Did you receive it? Do you receive it?
Yes, sir.
Okay, so we have discussed up to gate driver circuit. Okay, after that, another important simulation is simulations of different basic DC-DC converter circuits. Okay, so we know that there are different types of converters available in our in our markets or in our applications, different types of applications. Suppose you have started with AC/DC converter, means rectifier. Okay, rectifier, then control rectifier, uncontrolled rectifier, control rectifier, semi-controlled rectifier with different types of load. Okay, then we are discussing about the different driver circuits. Okay, what are the importance of the driver circuit? Why isolated driver circuits are more important compared to your non-isolated type driver circuits? Okay, everything I was discussed in my previous classes. Okay, as well as the some of you have done the simulations also. Okay, so I hope there is up to that questions there is no doubt. Okay, so we are having some special session. Okay, so in next week we are going to start that lab in offline mode. Okay, so the basic considerations are that when you are attending the lab, okay, you must wear the mask. Okay, mask is mandatory to enter to the lab. That is number 1 point. Number 2 point is that we are having some special session. Okay, so at that session we can discuss some of the pending some of the previous simulations. Okay, rediscuss means that you are getting an scope to re-simulate all those files here. Okay, another scope you will get. Okay, so those are facing problem. I think most of you are getting results. Very few percent are there. Very few percent, maybe 3-4 maximum. 1-2 or 3-4. Those are not. Those are facing problem. Their laptops. Okay, and sometimes software issues. Okay, they can get the scope to simulate their simulation in multi-sim platform. Okay, that's important. Second important thing. So third point is that today we are discussing about the simulations of different DC-DC converters. Okay, so we are starting with that rectifier. Then we are discussing now about the chopper. Chopper means if you have some DC input, so your output is controlled DC. Okay, so that means your input is fixed DC, but you want variable DC as an output. Okay, so what you need to do, you have to depends upon your chopper circuit. Okay, so there are different types of choppers. You can already you have gone through in your second year power electronics subjects. Okay, so basically we know that step down chopper, step up chopper. Okay, then buck boost. Okay, step down means buck type chopper, step up chopper means boost type chopper. Okay, then buck boost means both step up and step down can be possible, only variations of the duty cycle. Okay, so below 50% and above 50%. Both just changing of the duty cycle. Okay, their configurations, their working has been changed from step down to step up or step up to step down, like that. Okay, so that is your buck boost. Then these all are the choppers that is second order. Okay, only 2 energy storing elements are there. But after that we can see some other types of not other types, some derived converters. Okay, some derived converters means cascading. Okay, cascading of some DC-DC converter. Suppose cascade of that buck converter and the boost converter, like that. Okay, so if we cascade both the converter, then what happened? We can observe that their energy storing elements also being increased. Okay, so like that converter, we know that is Chuk converter is there. Okay, so in Chuk converter, 4 energy storing elements are there. Okay, 2 inductor, 2 capacitor. Okay, so that's why it's an example of a Chuk converter is an example of 4th order converter. Okay, Chuk, then SEPIC converter also be there. Okay, but the problem in the Chuk converter is that the polarity. Okay, output voltage polarity is different. Okay, it's reverse polarity. So what we are doing? So instead of Chuk converter, we are also using the SEPIC converter. The polarity of the SEPIC converter, it is not changed. Okay. So we can also use that unreverse polarity based converter, that is SEPIC converters. Okay. These are examples of a non-isolated type DC-DC converter. Okay, so we are also having isolated type DC-DC converter like forward converter, flyback converter, push-pull converter, okay, then half bridge converter and full bridge converter. Okay, so in this segment we are going to discuss about only step-up converter and its output voltage in open loop. Okay, first we are considering here in the open loop circuit. Okay, so first we have observed here or doing the simulations in open loop. Okay, for open loop study for buck converter, boost converter, half bridge converter and full bridge converters. Okay, so this example only taking here we are giving or providing the results only for resistive load. Okay, so you can also do the same simulations with different types of load. Okay, 4 basic converters are there, but what you need to do, you have to change the loads of different converter. You can use R load, RL load and RLE load and study your observations and prepare your observation table. Okay, how all the parameters are varying, so or the duty cycle of the converter is varying, what is your output voltage waveforms and what kind of changes you have observed here. Okay, that's at the very important observations for this study. Okay, so we know the basic structures of the converters, that all are the SMPS, switch mode power supply. Okay, so first we are starting with that buck converter. Okay, so here you can see the buck converter basic circuit diagram you can observe over here. Okay, basic equations. Okay, duty weighted, directly you are getting that one. So voltage waveform, current waveform you can also put over here. Okay, in any of the standard book you will get the theory. Okay, so directly following of the theory for this manual is not required. Okay, you can better follow any of the standard books, like suppose Ned Mohan books, suppose Rashid books, you can follow. Okay, the theory. Okay, and here you can see the circuit diagrams of the boost converter. Okay, and the output and the coil voltage or inductor voltage of the boost converter is given in that figures also. Okay, so when the switch is turned on, then what happens? What voltage will appear across your inductor? So input voltage minus, if the switch is turned on, means it is 0. So V in minus V0 equal to VL. So direct input voltage, that V in is applied, is appeared across your inductor for switch on conditions. When switch is off, then what happens? What voltage will appear across your inductor? So your output voltage minus input voltage. Sorry, your input voltage minus output voltage equals to your VL or EL. Now you know that for boost converter, output voltage always higher than your input voltage. So negative voltage. So negative voltage is coming across of your inductor. Okay, coming across of your inductor. So current is first charging, then discharging, charging, discharging, like that. So your average voltage. Okay, so your average voltage, but at the output load, okay, you will get the average voltage. So
Sir, your
average
voice is
between
not
positive half and negative. But your voice is audible from my end. Because am I audible?
Yes, sir. Yes, sir.
I think the network issue from your end. Okay, that issue is not from my end.
Sir, institute LAN
Okay,
issue.
and what happened?
Sir, your screen was frozen a little bit.
So session has been recorded. If you are facing any problem, okay, you can also listen my word also. Okay, from the recording that also been available. Okay, that whatever you are speaking, everything is clearly audible from my end. Okay, and I think some problem is there your side in between. Okay, that's why some network.
Sir, still
maybe
it is
broken
breaking.
sometimes.
Not clearly audible.
So what can I do? Tell me. Okay, so this is circuit diagrams of that boost converter. Okay. Then here you can see the basic circuit diagram in open loop for buck converter. So parameters are given in that circuit. Okay, you need to only simulate that value and see the what is your voltage waveform. Okay, so voltage waveforms means load voltage you need to find out and that current. Okay, load voltage and load current. Okay, here only resistance resistive load, the simulation is showing in the resistive load. You can also include that a resistance with series with inductance and resistance series with inductance plus back EMF. Both you can possible. Both kind of conditions is possible. R load, RL load. Okay, R load, RL load and RLA load. Okay. So parameters are given here. So for your help, so you directly when you are designing your circuit for in MS team, sorry, in NI multisim, so you can directly take this parameter value for the simulation. Okay, and here we can see the waveforms of the gate pulse. Okay, now dynamic response. Okay, so by you can see the transient, you have to fetch the figure such a manner. So transient waveform as well as steady state waveform, both should be visible. Okay, so here we can see the transient waveform initially, then steady state value. Okay, for voltage as well as current. Okay, both we need to take for every converter. So for first we are starting with buck converter. Then we'll do that. Then small calculations, how much values you are getting. Okay, so some basic calculations for designing the converter. Okay, and then we'll do for boost converter. Okay, and take that dynamic performance means steady state as well as transient. Both the waveform will be fetched. Okay, for your voltage waveform. First one is your voltage waveform. Second one is your current waveform, and gate pulse you can also take. Okay, this is your gate pulse. So first we'll start buck converter, then boost converter, then half bridge that we are talking about, asymmetrical half bridge. Okay, so asymmetrical half bridge, it's also a DC-DC converter. Okay, so you know that here we are using that RL load. Okay, the parameters values are given over here. Okay, we can see that two oscilloscopes are given. Okay, we can see the gate pulse pattern as well as output voltage and current waveforms. Okay, so this is your gate pulse pattern, both the converters, and it is your output voltage and that current waveform. So current is not, output voltage waveform is changing from 100 volt to minus 100 volt, plus 100 to minus 100. Okay, but your current, here you can see the current waveforms is not in negative. Okay, it is from positive half only. Okay, for half wave or asymmetrical half wave. But if you go for that full bridge configuration, that current also be negative. So as per the average, as per your gate pulse, okay, it's totally depends. The gate pulse means it's a 4 quadrant operations. Okay, so this is full bridge means 4 quadrant chopper. Okay, so 4 quadrant chopper means sometimes voltage are negative, sometimes currents are negative. Okay, first quadrant voltage and current both are positive. Okay, and third quadrant voltage and current both are negative, but both the cases power is positive. Okay, then it has been changed for second quadrant, fourth quadrant, one power will be negative. Okay, so one of the component means voltage or current, one of them will be negative. So it's a 4 quadrant operations of the chopper. Okay, so you know that 4 quadrant operations of DC drives. Okay, so we are also use that full bridge configurations as a chopper for that 4 quadrant operations of DC drives. Okay, that's why we are talking about different load resistance. First starting with R, then RL, and finally RLE. Okay, with variations of the gate pulse possible. Okay, so that's better. And prepare a observation table. Okay. And here we can see the gate pulses. of waveform. Okay, all the gate pulses are there. Of here we can see two legs are there. Okay, so diagonally the converters are working. So diagonally they are conducting means the same gate pulse. Another rest of the diagonal conductors will apply with some phase shifted gate pulse. Okay, here you can see current also varying from positive half to negative half. So both voltage and current both are varying. Half bridge only current is positive, voltage can go up to negative. Okay, so half bridge configuration only 2-quadrant operation is possible, but full bridge configuration 4-quadrant operation can be possible. Okay, so I hope all of you are able to get that idea. Okay, if you having any confusion, please let me know. I can rediscuss some of the questions. Okay, so I have already